Hello everyone. Let us study quadrature mirror filters, and we will also see after studying the quadrature mirror filters is that how these filters can be used to reduce the effect of aliasing in the filter banks. Now this is the block diagram to start with. I have taken the case for capital M equal to 2. That means I am considering only two filters in the analysis section of the filter of the system. To start with, take a full band signal, meaning by that Xn is a full band signal with sampling rate of f naught. And we send this signal to the analysis filters. H0Z and H1Z are the two analysis filters. For the generalized case, there can be more filters also, right? As in the case of digital filter banks, we can establish a full digital filter bank where the first filter will be a low pass filter. In between filters can be band pass filters. Last filter can be high pass filter. But to make our point for the case of quadrature mirror filters, I'm taking the example of only two filters in the analysis sections and two filters in the synthesis section, right? So we send this signal with sampling rate f naught to analysis filters to separate out the spectra in appropriate bands for which these filters are designed. So these will be the signals which will be decomposed by these two filters x01, x0n and x1n. These filters will produce some spectral shaping properties. Definitely, these filters will produce some spectral shaping properties to the incoming signal and will decompose the signal into x0n and x1n. To maintain the rate, because there are two paths now, to maintain the rate, we will decimate the signal, or we will downsample the signal by a factor of 2, such that the sum rate at this point, this line shows the sum rate at this point is f naught. So that means the sampling rate is downsampled here by a factor of 2, and ultimately at this point, summing these two the sample rate of these two signals, the total sum rate will be f naught. Now in between the analysis section and the synthesis section, which I will discuss just now, will be any processing that will be done by the system. The processing may involve the quantization, coding, or some kind of compression. And after that, the signals will be sent to the synthesis section. In the synthesis section, the signals will be upsampled by a factor of 2 in both the parallel paths, and we will use the synthesis filters f0z and f1z. F0z will be a low pass filter and f1z will be a high pass filter, as was there in the case of analysis section. So these filters will be used to synthesize the two incoming signals y0n and y1n, and finally these signals will be summed and will produce the signal yn. Right. Now let us look at what are the various characteristics of this type of system. Now, the decimated signals V0n and V1n, so these are the decimated signals V0n and V1n, are coded in such a way that the spectral properties of the subband signals are exploited. So that can be coding, or that can be compression, or any other algorithm that you want to do here in between the analysis section and synthesis section. That processing will be done, and these properties, so the certain properties of V0n and V1n can be exploited. Maybe it may be energy levels, right? Because you may have to do the processing where more energy levels are required for, let's say, low pass section of the parallel of the path, and maybe less energy is required towards the high pass filter, because ultimately you will have to uh, you will have to base your ideas on the perceptive importance. For example, in hearing process, the response of the ear is logarithmic to various increasing frequencies, and we don't place the same resolution to all the frequencies. Certain frequencies need to be enhanced in comparison to the other frequencies, so that there is a factor of perceptive importance that will come into the picture. So exploitation at this point will be based on the perceptive importance, that how the signals will move ahead towards the synthesis section, so that we can have a meaningful idea of the output, meaningful idea at the output. We want to look at the information according to the perceptive importance. Right. So based on this intuitive idea, the type of filters that come in mind are quadrature mirror filters. That means we will use in the analysis section the quadrature mirror filters, and same can be used in the synthesis section of the system. So these quadrature mirror filters will have the crossover frequency as pi by 2. So these are the frequency responses of the two filters, H naught e to the power j omega. So that means this is the magnitude response of the low pass filter, and H1 e to the power j omega is the magnitude response of the high pass filter. Now, so this is a low pass filter, this is the high pass filter. The point of crossover, that means we call it as the crossover frequency. So that is pi by 2. That's why these filters are also known as quadrature filters. And you see, the high pass filter is a mirror image kind of frequency response of the low pass filter. So these two filters are known as quadrature mirror filters, because the crossover frequency is pi by 2. So that is why the term that explains the term quadrature. And because the frequency response of the high pass filter is a mirror image of the low pass filter, so that explains the uh, mirror word in the quadrature mirror filter um, type. Now, if H naught is a very good, let's say if H naught Z, that means the low pass filter transfer function is a very good low pass filter, then mirror of this filter will be high pass, and these will be a quadrature because their crossover frequency is pi by 2, as shown in the figure in next slide. That I have already explained, that why these two filters are quadrature filters, and why we call these two filters as the mirror filters. All right. Now, what is the ultimate goal? Ultimate goal is to, if you look at this block diagram, you have an analysis section, certain processing section will be there in between after the decimation, and then you have upsampling and the low pass filter, F0 Z and F1 Z, they constitute the synthesis section. Now, Xn was the input signal and Yn is the output signal. The goal that I'm going to discuss is that goal is to build analysis and synthesis filters such that the reconstruction of the signal in the end is perfect. That means the Yn signal which is being reconstructed here at the output should be as close as possible to the input signal. That means there has to be the idea, the goal is to have perfect reconstruction of this signal xn at the output. So we can designate this signal as x hat and also. So that means yn is as close as an approximation as possible to xn. So that's the goal. We must have the perfect reconstruction possible. Now, the reconstructed signal, which is x hat n, right, can differ from xn. Now, if you see this block diagram, if yn is equal to x hat n, now in what ways x hat n can differ from xn signal? Right. What are the various types of distortions while traveling through this block diagram this xn can have, so that x hat n will differ from xn? So let's look at the various factors which can distort the signal xn. Right. The first thing is the aliasing. Right. Aliasing is one factor which certainly will be there because the two frequencies responses of the filters will overlap with each other. Then there can be amplitude distortion, there can be phase distortion, right? And processing, while going through the processing, there can be more distortions possible when we are going through the quantization in itself introduces some kind of noise. Then I mean, the signal xn while going through the block diagram can suffer from various artifacts, and which for because of which we will get x hat n, which is we are trying to be an exact signal as xn, but we will have to design the analysis and the synthesis filters in such a way that we achieve our goal, right? Now, as I said, our goal is to design synthesis filter to overcome these limitations. Now, in practice, analysis filters have non-zero transition width and stop band gain. Of course, the transition width of the filters will be non-zero because there has to, you cannot achieve an ideal filter using the practical components or practical by applying the practical scenarios available. You will not be able to achieve an ideal filter. There will be some role of, there will be some transition width, and there will be some stop band gain also. So in that case, let us look at two scenarios. The first scenario is this filter in which the stop band attenuation is sufficiently large, right? If you look at the stop band stop band part of these two filters, the attenuation is quite large. But effect, but what is the effect of having large amount of stop band attenuation? There will be very less aliasing because the two frequency responses, the two spectra are not overlapping with each other. So therefore, aliasing is not predominant if the stop band attenuation is sufficiently large in the two filters. But there is a sphere attenuation at pi by 2. Of course, there is this sphere attenuation at pi by 2. Now, the problem is that when, if you use these two filters at the analysis side, and because you need to synthesize, you need to pass the signal through the synthesis filters also. So once the synthesis filters will get this kind of will get a kind of signal which has gone through filters with these responses, the upliftment of the signal will take place, will have to be done by the synthesis filter. That means the amplification of the signal has to be done at the points where a huge amount of attenuation has already taken place. But due to that, the noise will also be amplified when the synthesis filters will try to do the amplification of the signals where a lot of attenuation has taken place. So noise amplification will be a problem as synthesis filters will have to boost the gain. Now, in that case, uh, because you want to have you want to have no aliasing, so filters to be designed have to be very expensive. And secondly, noise amplification will also take place if you choose these two kinds of spectra for the filters in the analysis section. All right. Now let us look at the other scenario where the two spectra are overlapping. So overlap is there and the crossover is pi by 2. Overlapping filter responses. So these two responses of the filters are overlapping with each other and there is a crossover frequency at pi by 2. And of course there is a possibility of aliasing because the two spectra are overlapping with each other. So there is a possibility of aliasing. Now, if synthesis filters can take care of the aliasing problem, now if you design the synthesis filters, such synthesis filters, if you choose such combination of filters where you can take care of the aliasing problem that has occurred due to the overlapping of the spectra, then there is gradual attenuation at pi by 2. So there is very gradual attenuation at pi by 2 because you have allowed some kind of aliasing, But if the design of the synthesis filters is such that you can take care of the aliasing problem, then in that case there will be very gradual attenuation at pi by 2. So therefore noise amplification, because since the attenuation is not large here, noise amplification may not be that bad during the synthesis. So these are the very important distinction or differences between the two types of responses. One is this kind of response, the other is an overlapping response, right? So we will use this kind of response, and we will try to we will try to design the synthesis filters in such a way the aliasing problem is handled. Okay. Now we can say that we will design the synthesis filters, but unless or until we do not derive an expression for the synthesis equations, then only we can reach to some concrete solution that yes, we have been able to take care of the aliasing problem, and the filters can produce there is a less possibility of aliasing, and there is gradual, so noise amplification will be avoided. So we will have to make a derivation of an expression for reconstructed signal, right? Now xkz, let us derive the expression. Xkz is equal to hkz into xz. Now what is this? If you look at the starting block diagram, so you have xn signal. If you take the z transform, it will be xz, and you decompose this signal into two signals, x0n and x1n. You take the z transform in both the cases. This 0 and 1 subscripts will be represented by an index k, right? So you have xkz equal to hkz into xz. So that's what we can explain it from here. This is this h0z and h1z basically fall under hkz, x0 and x1n fall under xkz, and xn falls under xz. All right, so we can say that hkz equal to hkz xz, where k is equal to 0 and 1. Now we are choosing a downsampling factor of 2 only. With capital M equal to 2, the output of the decimator is, so vkz will be given by half xkz to the power half plus xk minus z to the power half. If we apply the decimation by a factor of 2 and we take the z transform, so the z transform will be half xk z to the power half plus xk minus z to the power half. Basically this is the aliasing part, so we have to actually minimize, we have to somehow make this part 0 so that the aliasing can be avoided. Now uh, you get you get v naught and v1 here, after decimation you get vkz's basically, and then you will have to do the upsampling, and then you will get ykz. So let's see. So post expansion or upsampling, so after you apply the upsampling process, you get ykz where k will be equal to 0 and 1. So this is how we take care of the expansion or upsampling by a factor of 2. You will get vk z square. Now what is vkz? Vkz is this expression. If you transform this expression into vkz square, so this half power will become full power. Half is equal to xkz plus xk minus z. So that is after that is post expansion or post upsampling. All right. Now, since you have xkz here and xk minus z here, so you also know that xkz is given by hkz and xz. You replace xkz with this factor plus and xk minus z with with hk minus z into x of minus z, right? So because you replace the z with minus z. Now reconstruct it finally in the block diagram. After the upsampling, you will have to pass the signal through two synthesis filters. Now your reconstructed signal x hat z will be equal to F naught Z, which is the first synthesis filter, which will be basically a low pass filter, into Y naught Z, plus F1Z into Y1Z. All right, so that's the response you get at the reconstructed signal. Actually, we have to look for this signal and we have to see whether the design process is such that we have been able to avoid the aliasing problem or not. Now, you have Y naught Z. So this is my YKZ, right? You replace you Y naught Z. You put the values of Y naught Z. What is Y naught Z? Y naught Z will be equal to half xk x naught Z plus x naught minus Z, right? Uh, so you will get uh, half h naught Z f naught Z, right, plus h1Z f1Z into xz. This is the first term that you will get. All right. The second term you will get is half h naught minus z f naught z. We must force this. Yeah, I'll come to that part. And h1 minus z into f1z and x of minus z. If you substitute all the values, you will get this expression. Right. Okay. Then after that, so you have two terms because one term corresponds to h of naught, the other term corresponds to h of 1. All right. So you do certain manipulations and you will get this term. Is that clear? Now what you have to do is this term with minus z is actually the aliasing term. So this is a normal response term of the synthesis filters. This is actually the aliasing term. Now we must force this term to 0. We can write these two equations with plus sign here, this one and this one, in the matrix form. By this is 2xz. We will take this xz and x minus z here. This is a row vector. Then h naught z, h1z, h naught minus z, h1 minus z, and f naught z, f1. So we have put the equations in the matrix form, and this matrix h naught z, h1 z, h naught minus z, and h1 minus z, this matrix is known as alias component matrix, right? And we have to actually avoid the aliasing term. So let us see how can we do that. Now for alias cancellation, this term h naught minus z f naught z plus h1 minus z f1 z, this has to be put equal to 0. Now this h naught minus z and h1 minus z, right? How can we put this term equal to 0? If we put h naught z as h1 minus z, right? We put h1 minus z here, and we have to make this plus sign minus, and we put f1z as h naught of minus z. So if you substitute the values of f naught z and f1z with these two values, you will see that the whole aliasing term will go to 0. So that means alias cancellation will be achieved. Now that means alias cancellation will be, now that means given h naught and h1 for the analysis filters, please remember that this is very important discussion. Given h naught and h1 as analysis bank filters, we can obtain f naught z and f1 z as explained above. We will, what, f naught z will be equal to f1 z, f naught z will be equal to h1 minus z, and f1z will be equal to minus h naught minus z. That means if we know, first of all, if we know h naught, we can derive h1. And if we know these two responses, then we can design f naught and f1z as explained above to remove aliasing. So we are designing h naught and h1 as QMF filters. Because if we can design h naught, which may be treated as mother filter, then we can design all other filters, right? So what we will do is we will design H0Z and H1Z in the analysis filter as quadrature mirror filters, and we will try to design the synthesis filters in such a way that we will be able to make the aliasing term zero. Rather, we will be, in fact, we will be minimizing the aliasing present in the signal to a bare minimum value using the quadrature mirror filters. Therefore, with the quadrature mirror filter design and given H0Z, only H0Z is required, because if H0Z is given to you, you can obtain H1 also, and further you can obtain the synthesis filters also. We can construct and populate all other filters towards alias cancellation. So that's how the quadrature mirror filters will be used to avoid cancellation in the system. And we can, here if you see, we have done it, we have designed this system for two filters. That means, and we can generalize the design to capital M filters also. And there we will have to decimate by a factor of M and upsample by a factor of M. Right. With this, I finish this lecture for the QMF design. Thank you.